Hello, today we are going to talk about materials and prototyping of compliant mechanisms. Throughout the course we have seen a number of prototypes, a number of devices, and we have shown the video clippings of how they do, and we actually showed you about 80 compliant mechanisms that we have in our collection, our database. You may wonder how these are made, especially those of you who want to work on compliant mechanisms. You should know what materials you can use to make them and what techniques you can use to make prototypes or even manufacturing. So, let us look at both of these aspects now, materials and prototyping. And now we have compliant mechanisms at all sizes, and what materials are used. You can see a human hand here, so you know that it is large, and there is a microscope objective here, you know that it is small, and even if you see a SEM, you know that these are small anyway, and you have something that looks like an SEM, but it actually focused ion beam machined silicon that is actually at a very small scale, sub micron or nanometer. So, size does not really matter for compliant mechanisms. You can make it at any size, you just have to choose the appropriate material. So, what materials are used for compliant mechanisms? Most often we use polymers, the plastics. Plastics are two kinds, polymers and elastomers. Elastomers are more like rubbers. In the last lecture we discussed these fluid filled elastomeric enclosures are free. So, these are elastomers, meaning rubbers, which are very flexible materials, sometimes people call them soft materials. With those you can make interesting compliant mechanisms, and we have done that also, as you will see examples, but most of them are polymers. But we have also used metals, as we will see some examples today, and we have seen it throughout the course, and ceramics too, they are not excluded, and then silicon at micro scale, because lithography exists for making interesting miniaturized compliant mechanisms for micro electromechanical systems. In fact, any material can be used, and you can use composites also. So, no problem, in fact they are good because you can exploit their anisotropy for making interesting compliant mechanisms. So, if you look at the different class of materials, pretty much everything. I have not written natural materials here, but people have been making compliant mechanisms using natural materials like leather and wood and so forth. The ancient, the bow and arrow, the bow is actually a natural material, and that is a compliant one because the energy is stored when you bend it, and that is what you get it, and also in the string. Okay. So, natural materials can also be used, but today we do not use as much because of lack of consistency in the material, but this is not excluded. Basically you can say that just about any material can be used to make compliant mechanisms. And one concern that anybody would have while choosing a material for compliant mechanism is that if I make this material, will it not break? So, that will always be an idea, especially when I say there is ceramic, then you wonder whether it is going to break or not, especially brittle materials. Now, silicon is a brittle material, and one would think that it is going to break, but see that it does not. What I have here is I am holding a silicon wafer here, and what we will see is that if I play the movie. So, what we have done is in the silicon wafer we have cut a spiral, a square spiral. Okay. It is all in one plane, and you can actually see that I can move it, and it actually starts vibrating, and we can press it this way, that way. So, you have actually silicon wafer here, which is very brittle. If I drop it, it is going to break into pieces, but we can make it flexible. So, let me play that video again. So, we are able to make that. In fact, it is like a silicon slinky. I can take it and move it up and down, which I have in my hand, not silicon. So, what I have here is an acrylic piece which I had shown earlier, and it is just that on the side I have just attached this rod, so that I can pull it. Yeah. So, this is actually acrylic piece with a laser we have cut here, into a circular spiral. So, it is all acrylic piece there, and it just the rod is just attached, right. You can see the other side, and now I can push it in and out, and I can make it, it is very flexible. It will not break because its design is such that the strains are not high or stresses are not high, but the displacement is very high. So, I always argue, I have not made one so far, is even if I take a slab of granite and if I cut a spiral, I can make that a spring, something like this. So, it is a question of design. If we want to achieve compliance or flexibility, nothing to do with material. Okay. Of course, you have to design according to the material property. So, what prototyping techniques can be used to make compliant mechanisms? A number of them are listed here. So, we can do milling, take a sheet and cut. So, most of the mechanisms that we have made are used by milling, are made by using milling. So, you can take mill bits of various diameters depending on the minimum feature size that you have and cut it out. We have also used wire cut electric discharge machining. So, that is for material that are conductive. So, that can be done for metals. I will show some examples. One can use water jet cutting and molding, like injection molding. You can also do extrusion, especially when you have planar compliant mechanism, make an extrusion, the whole mechanism will come out, and then we can just slice to make, that will be a batch production type of technique. So, all of these are batch production amenable, and we can do punching and blanking. So, that will be an interesting thing, we will see that. And sheet metal bending, you can make something in a plane and then bend it out of plane to make interesting 3-dimensional compliant mechanisms. Just about any technique, I just put dot 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 saying that anything that is there, you can adapt it for making compliant mechanisms, because we just need to take a material that is available and cut out some shapes into it in order to get the design that we have for compliant behavior. You can use laser, chemical etching and lithography and chemical etching combined for miniaturization. So, these are also possible. So, there are a number of techniques at large scale and small scale, small sizes one can use to make compliant mechanisms. So, let us look at some example. Macro size, we have this mechanism polypropylene. Among the plastics, we use polypropylene a lot because it has the right low characteristics of having low Young's modulus and high strength. So, polypropylene is also is available widely, and that is used here. This entire mechanism was done by milling out of a large sheet. Okay. There are very thin beams, but milling can be done, and here is a metal one, and this is a 3D printed one. These are all large. This is actually aircraft wing. So, very large ones also can be done using compliant mechanisms. We have seen those examples already. Now, we come to slightly small, then we have this the metal one. So, it actually being pulled and you can see that moving. We will see a larger one, and here is a ceramic. So, this particular one is to increase the fracture toughness of armor. So, there is a little, not really a lot of compliance, but enough to increase the fracture toughness, and this is a 3D printed one that we saw at the mesoscale. Already we saw the video of this where it grabs something and stretches it. And then we have micro. So, this is actually I would say the one that was made in 1994, or actually less than that, 1993 I will make it. So, it was done back then. It was my first micro compliant mechanism, most likely the first in the world as well, and more recently accelerometer, where things are, you actually do not see these beams here. There are tiny beams which are only 5 microns wide. So, at that time here it was more like 15 microns wide back then, even though we could have made small, but it was the first one to try. and the micro level lots of things can be made out of silicon. So, this is silicon. Here is one that is actually nano. This was done using focused ion beam milling. It is like milling, but you do with ions, and this was more like 2 microns. So, you can imagine the other features. So, these are small fluxes here which are very small. You can do the focused ion beam milling to do that. These are more recent work where we have high aspect ratio structures that we are using in some cell culture scaffolds. So, you can have very high hexagonal structures and various other things. This was done using some kind of super resolution lithography. So, let us look at a few examples to look at macro, meso, micro and nano, and how materials and prototyping techniques come together to make compliant mechanisms that are interesting. This one, as I already discussed in another lecture, so this was to have a cemented sand specimen here with hand force. Anybody, when a kid can press these and crush this cemented sand specimen. So, because this is an FEACM, what we call composite compliant mechanism, and then here we have a DACM, displacement amplification compliant mechanism, that based on the force it will move this way very large amount. You can put a Hall effect sensor, measure the displacement and measure this force. Okay. So, here we used basically milled thing here. Eventually, if somebody wants a product out of it, can be injection molded. So, here is the video of that. So, cemented specimen is over there, we are applying force by hand. You can just see a couple of fingers, you cannot even you can hold it, of course, you cannot really crush with your fingers, whereas the FEACM enables you to do that. And here is one that was made with wire EDM, looks complicated. It was aluminum or spring steel, very complicated device, lots and lots of beams, and it was made in 2 layers. It is an XY stage with enhanced range. So, metals also can be used very happily. This one we have discussed in the context of static balancing, where we have this I have to use a different color. Yeah, we have these beams here which are spring steel strips, and then there are aluminum brackets. So, aluminum bracket, let me put in a different color. So, these are aluminum brackets. So, here here also I have forgotten couple of more spring steel strips. Here is one, here is one. So, we can make with metal also. It is not single piece in the sense that you can just take one and bend it, which you could, but we happen to see that this is a better way of doing here. Professor Prasanna Gandhi at IIT Bombay is doing a lot of work on making compliant mechanisms using this type of technique. Now, let us look at a couple of examples of mesoscale, something that centimeter to about 100 microns, not really micro, but bigger than that. So, this is the metal one. So, this is about this will be I think 2 centimeters. So, here this was like more like 1 centimeter, and this probably was yeah, maybe quarter of a millimeter or something like that. So, you can see this metal and highly elastic, we have put a little hook, but you can do with your hand also, make little a gripper. Okay. So, it is a spring steel gripper. So, what you have here is a spring steel gripper that we looked at how it works, and now let us see how we can make it. This was made using wire EDM. So, very narrow reentrant kind of structure was all cut using wire cut electro discharge machining, but this will not be amenable for batch production. How do you do this using batch production, meaning something like an assembly line, all of them should just come out 100 per second or something like that. So, one can explore adapting the existing manufacturing processes at the large scale to meso scale. So, the idea is that can we make this gripper by punching or blanking. So, there is one hole here and there is hole, this one hole, by that I mean a hole like this. I can punch that and I can punch the one in between, and I will be able to make this using like a batch production processes, because the laser whatever you do, it is not going to be economical, whereas punching is economical. In fact, that is what we did. So, we can go from 100 microns to a millimeter or centimeter scale devices very easily with this punching. For that you need to have this is wire-EDM, this will be very expensive, very slow, but then you see a lot of craft punches that are there now that we can buy in the market, craft punches. So, here is one that has the maple leaf die. You can punch out of metal. We have done this in paper, that is 150 micron thick paper, and then there is aluminum foil. You can cut these various shapes. Okay. And what the question we asked is that how narrow a beam can we punch, so that if I want to leave a beam there, I have to punch this hole and that hole. Okay. Or for making this compliant mechanism, I have to make this big hole here of a complicated shape, another hole over there. Then I can make this, two holes, but that will be quite difficult. So, but by splitting into several stages, you can actually get this done, which is what we ended up doing by making the gripper that I showed you. First we take a sheet and blank it out. So, we get this first stage. Now we are making a square thing, and the punch for that die for that is shown there, and there is a matching punch for it. And then we make another die which is like that, which is going to punch this hole here. So, we get that, we get this thing out of this here. So, when you have that, we make this hole. Okay, that is one punching operation, and then take this to the next level and take this device. Now, what you punch out, that will be there, that you throw away or use it, that is another idea. So, we have taken this thing here and punched one hole. Then you go to the third level where you have another little punch to make this one now, because previously, so we have done up to this. Now, we have to make something more here, another hole, and that is done there, that is the third stage. Fourth stage is this particular hole. So, this particular one, so you can actually cut this out. So, with this one you punch it out. So, this is the die for it. So, you can make that, this is the 5 rupee coin, and you can make this in 4 stages, you can do it, but 4th stage we actually ended up using spark erosion, because already there are these very thin beams are there, and when you punch you might actually bend them and break or whatever. So, we actually use this die and use spark erosion rather than wire-EDM. So, that is going to be slow, but our idea was to explore this and take it further. In punching we also did a lot of modeling to see what is the narrowest beam that you can punch and what is the aspect ratio of it, that is what the thickness, there is a thickness for this. So, if I take thickness divided by a narrowest feature, that is W, making it equal to 1, one can just use chemical etching, that is not a problem, but we want it to be as large as possible. We are able to achieve 2. The idea is with punching, can you punch into thick materials and have a very narrow beam left. So, very narrow beam. So, if we can adapt both punching as well as sheet metal bending, we can actually make very interesting compliance out of metal, which will be meso scale, and that is the going to be competitive against lithography based MEMS sensors, accelerometers and gyroscopes and so forth, those sensors are small, but when you put the electronics and package and everything, this is going to be meso scale, they are not going to be micro scale, they will be millimeter, centimeter scale. But the sensor element does not need to be small if there is a batch production technique such as punching. The advantage of a batch production such as punching is that even if the size of the lot that you want to make is only 50 or 100, it is economically justifiable, whereas lithography will not be justifiable. And the whole die set that we made for this application was not exceeding 30,000. Okay. So, it is possible to adapt existing processes for making compliant mechanisms. And this moving on to micro, we have lithography. We will be looking at this micro machined accelerometer in a case study little later towards the end of the course, that is next week. We will look at this and we will discuss how we can make at the micro scale, and there is a close up view, we will see the movie. So, you can see these things, they are so thin, they are more like wires or strings, but it is silicon and it does not break. We have used it, packaged it and all that, it works, and most of the beams in micro electromechanical systems devices are really thin and they work, and you do not have to worry about they breaking. So, here is a 2-axis accelerometer, details later in another lecture. So, it is all packaged into where we have the ASICs for electronics and mechanical chip is over here, and on a ceramic substrate, and it is packaged and it works as long as you want. We also have these miniature grippers, there is another lecture on that, where we use this SU8 and PDMS material. This is PDMS, where we can make grippers with which we can manipulate biological cells, as we will see in a future lecture. And here we have the process for making this. So, it is just lithography, you deposit the material and pattern and create the shapes that you want as a multi-layered structure. We want to nano, we have this focused ion beam milling machine which I had shown, but this one is sort of a super resolution lithography, where we have single photon multi-layer nanolithography using SU8 material, where you can get very high aspect ratios, details of which you can read in this paper. So, minimum feature size was 200 nanometers, and the length of this was very high. This is this line that you see here, this line, that is 2 microns. So, clearly the height of this is much more than that, whereas here if you see, this is 100 nanometer, this little line that you see there at the bottom. So, I do not know whether you see, the little line is 100 nanometers. So, this one is more like 100 nanometers, this is 2 microns. So, you have such a large 2000 nanometers is 100. So, you have the aspect ratio, and you can in fact you can go aspect ratio of as much as 250 also here. Okay. And if you go down to biology at nanoscale, you have actually proteins. These are also in a way compliant mechanisms, and in fact some of the design technique that we have for compliant mechanisms can be applied to these also. These are simulations taken from Professor Greg Chirkian's lab at Johns Hopkins University, but there are a number of them like this. So, they basically move, they are compliant, they are not like rigid body segments put together with joints, and proteins are really wonderful nanoscale compliant mechanisms, and the way nature makes them is a very efficient prototyping technique, which we cannot, but nature does. So, to summarize, almost any material can be used to make compliant mechanisms, and that almost any underline, any material can be used. It is a question of getting the right design for it, and number of prototyping techniques exist. Whatever is there, you can use it to make, and 3D printing, that makes your life easy, and this is in making the interest in compliant mechanisms grow, because just about anybody can make that now without much effort. Otherwise, when you make with milling, you have to have the right fixtures and so forth, but with 3D printing you can do, but then 3D print technology has a lot to grow because right now you do not have the properties being constant for a period of time. So, you can make and after a while things actually change their properties, but 3D printing technology will improve. At that time one can design and make compliant mechanisms rather easily. Okay. Thank you.